Welcome back to the Infinite Square Lab. When you watch mainstream market reports on the quantum computing sector, you are almost always shown a standard comparison of qubit totals. The media treats quantum scaling as if it's a routine software and silicon optimization race. But if you approach this field from the perspective of pure atomic physics, you quickly discover that the real world is not over algorithm design. It's a physical battle against quantum decoherence. Qubits are extraordinarily volatile. The moment external environmental noise touches a quantum processor, the superposition state collapses and your computing performance drops to zero. The industry has split into two conflicting physical paradigms to solve this. Let's bring up the lab monitor to analyze IonQ's atomic strategy against the rest of the market. Let's analyze the left column of our architectural schematic. This represents the brute force approach, utilized by industry heavyweights like IBM and Google. They manufacture artificial superconducting qubits on typical solid-state silicon chips. Because these qubits are artificial, they are inherently prone to manufacturing by variations and microscopic structure defects. To isolate these highly sensitive circuits from thermal noise, this system requires a massive piece of infrastructure known as multi-stage dilution refrigerator. Look at the temperature progression on the diagram. It transitions from room temperature down to 40 Kelvin, then 4 Kelvin, all the way down to a fraction 15 milli-Kelvin at the processing phase. This is colder than deep space. This path is an engineering bottleneck. To scale up, you have to build increasingly massive, structurally complex refrigerators, combat raw thermodynamic heat transfer. Now, look at the right side of our monitor. This is the IonQ's approach, the trapped ion architecture. Notice the total lack of cooling tanks. IonQ doesn't build artificial qubits on silicon. They use nature's pre-built qubits, single atoms of elemental ytterbium. To hold these atoms perfectly still without physical contact, they utilize a linear pole trap. This device applies dynamic radio frequency electric fields governed by Mathieu equation. This creates a stable electrodynamic potential well that suspends a uniform chain of identical ions right in midair within an ultra-high vacuum chamber. Because these atoms are perfectly isolated in a vacuum, they can maintain quantum coherence at standard room temperature. Instead of routing signal wires into a giant freezer, IonQ routes focused laser arrays through integrated photonic chips to program the system. They steer quantum states using laser pulses to drive Levi oscillations, manipulating collective atomic vibrations to perform complex calculations. This structural divergence completely transforms the investment thesis. Building superconducting system is a mechanical, heavy industrial infrastructure challenge. Scaling up requires handling immense thermodynamic cooling loads. IonQ's path shifted the paradigm entirely, from heavy refrigeration engineering over to high-precision optics and photonic packaging. By leveraging the fact that every single ytterbium ion in the universe is already structurally identical by cosmic definition, they bypass manufacturing defect corrections entirely. Their long-term mode relies on shrinking laboratory optics onto specialized photonic chips containing integrated waveguides, converting quantum computing into an optical lithography game. If you want to track how these advanced physics modes continue to redefine the technological and financial landscape, make sure to read our full comprehensive deep dive article linked down below. Make sure to hit that subscribe button to join our network here at the Infinite Scale Lab. Drop your thoughts on the trapped ion strategy in the comments, and I will see you on the next deep dive. Thank you.